All right, welcome back. So I'll continue the discussions a bit further. So what we'll look at today or in this session is how to evaluate the models, everything that we have learned so far. Is it actually working well? How do we try to improve the performance by looking at the metrics? Just as a quick recap, I don't think I should do anything more. Professor Nain did a fantastic job. She explained every single concept. So this is the simplified, overly simplified diagram of what's happening inside a network, one single layer, and you had two inputs, and then we ended up discussing about the chain rule as well. So since she has covered this part, I would not touch upon that again. But if you have some questions about this, we can always have a discussion later. Okay. So typically in any kind of deep neural networks, right? What happens is that we don't have just one layer, we have multiple hidden layers, and then there is this feature learning which she was talking about. There are some layers which are dedicated to identifying the edges, some layers which are dedicated to identifying the patterns, and so on. And everything put together, you are learning the patterns, right? You are understanding the pattern of the image. And then there are some issues. I think already Professor Nain mentioned about this in terms of vanishing gradients. And then there is a problem of overfitting, which we'll talk about it in a couple of minutes. But just to visualize everything that's happening here is that you have this inputs, number of inputs x1, x2, x3, and then you have a number of outputs that are y1 and y2. So at any given point of time, there is one layer getting activated, right? So in this case, you see that the hidden layer number A1, A2, A3, A4, those get activated in the layer 1, uh, referred by the superscript. And then the same thing when it goes to the next part, you propagate that particular weights further down to the next layer, which is A2. And then at the end of the day, you are coming back with coming to compute these final predictions, which are Y1 and Y2. So what exactly happens in this whole cycle? You have this Z1, which is nothing but W times X plus B. And then you have the first layers, which are typically the sigmoid of Z1. And then you have another layer, which is Z2. And then you have A2. And then finally you have Z3, which is final combinations. And then you say, now make a prediction on given Z3. And as you can see here, there is really no constraint about how many layers we would have, right? So you can keep on building number of different layers such that until you reach a good performance. So this is there is no magic rule for this. So many people try and test out different kind of architectures, different layers, configurations, and then they decide, okay, this is working better. So for now, we have a number of different architectures which are very well tested in the last 10-15 years. Some of them are AlexNet, ResNet, EfficientNet, MobileNet, and so on. So these are very standard architectures and they work pretty well. Okay, so then let's just take a quick look at this one. So as it was already explained in the board, you can see that they're exactly the same formulas that I'm having here, right? You have a W, you have a, then you have a bias, that is B, and then everything leads to a prediction output, AL. And then when it comes to the convolution itself, just for the sake of simplicity, for the common understanding, let's start with a simple image that is 4 cross 4, right? So if you have an image which is a simple grid like 4 cross 4, then you start convoluting this. So how do you convolute this? It's again, those of you who have taken signal processing, you have done this convolution in number of occasions, right? In signal processing, 1D signals, and it's exactly the same thing. So we have a filter, and this filter is typically learned in the case of neural networks. But you could also have these handcrafted filters, right? So in the olden days, you would use LBP, BSIF, and filters like this that had specific properties. And now in the deep neural networks, what you do is you try to learn the filter itself. So you start with this convolution filter, and then what you do is like you place it on the bottom left corner, and then you keep on sliding it, right? So every time you slide it, you get a new configuration. And then you can do it in overlapping manner. So I have first recorded the response of these 4 layers. Where is my mouse? There, here. So this filter overlapped on this one, 1, 2, 3, 4, then you get a response. And then you do the same thing with this one, it's like 1, 2, 3, 4, and then 1, 2, 3, 4, right? So you have three convolutions, 1, 2, and then 3 convolutions, right? So, and then you propagate it also in the vertical direction. So once you have this, so this image typically ends up in a much smaller image, considering that there is what do you call the padding happening to take care of the edge parts. And then you have this final feature map. This final feature map has to undergo some more transformations, right? And then what do? We don't want to deal with the high dimensionality of data, which becomes very tedious, right? It's, if you're talking about images which are of millions of pixels, and that will be very expensive operations. So what we do is that we try to extract the key elements from that one by doing a simple max pooling, right? Now again, the pooling concept itself has a number of different variants, but the idea here is that from this filter, I could simply say, okay, from all these four, pick the highest one, right? The maximum value of those four blocks, and then the maximum of these four blocks. So when you pick this kind of filters, pick this kind of values, then what you're ending up is you're ending up with something like this, much smaller, something that is manageable and that's more meaningful. And then comes the last part, because of the nature of the predictions that we are making. So we flatten it typically, right? So now the flattening is nothing but take these pixels and organize it in a linear manner, right? So then we are converting it into flattened vector, and this flattened vector is passed to the fully connected layer, which is having the total number of neurons based on the number of classes you have. So if you are learning an image, if you are learning a network for, let's assume, differentiating between cats and dogs, then you would have 2 neurons. But if you are going to differentiate between 10 different kind of cats, 10 different families of cats, then you would have 10 different 10 neurons, 10 output nodes in the last part. Okay, so this is general working of fully the deep neural networks. And now, given that there are also a lot of works happening in this direction, I also would like to just give few words about RNNs. In the case of RNNs, is that you are also not just taking the current instance, but you're also taking the previous instance, right? So it's a sequential data. For in the case of speech recognition, so if I'm trying to say, I would like to go, and then it could be filled up by like to go to eat, right? I would like to go to see Jaipur, right? So and then you have certain kind of context, and then you can fill that one. And how it works is typically very high level diagram is like this one, right? You have a particular state that is h0, and then you have an input x1. So based on the h1, h0, and x1, you're going to predict y1. And now that you have this in the second one, what you can do is you can make the next prediction for y2 based on the previous data and the current data, right? So you're sequentially improving the network. Okay, so this is again, now the whole idea here is that what changes is the way we deal with the data. In the deep neural networks, we were convoluting it and then taking the features and then passing it to the final part. But in the case of RNNs, we are doing it in a sequential manner, and also the data is not typically images, it's signal processing data, right? I mean 1D data that we are talking about. Good. So whenever we are talking about any kind of these networks, there are two things that we often come across. One, it is called as overfitting. Overfitting is something illustrated here. As you can see that there are a number of data points, and let's assume that there are two classes in this case. And then if you are trying to fit a curve for that, very crude way would be to draw this line, this blue line, right? So, and then you can say there are two classes that are very well separated. Now, what happens with this blue line is that you have not covered all the data points that you have, right? Which means that if your network is not able to figure out all different samples that are in the training set, so you are underfitting it. And then you can be very creative, and then you say, okay, you know what, I'm going to try to make the model more sophisticated, and then you're going to fit every single point that you have from here. You start on the red curve. Oh, sorry. here on the red curve. So you can see that this curve is covering every single point that we have. But then what is the problem here? Then we are overfitting it, right? So if there is a new sample that comes, and this network will not be able to, it will not be able to deal with the new data. So always be careful about two aspects, this underfitting and overfitting. Whenever you train a new model, your model will give you very good results on the training set, but then when you put it on the testing set, which is unseen, then your network starts behaving erratically, right? So the problem there is mainly because of this underfitting and overfitting issues. So what do we do about this one? So these are two things that you can't really solve, right? It is something that we have to live with. You can come up with strategies which help you to make it better, make it more robust by training data in a different manner, by augmenting the data, or by injecting the noise into the data and retrain the network and so on. But no matter what you are going to do, there will be some of these aspects that you will encounter in any training. So how do we deal with this one? So then is the two paradigms which are typically looking at this errors. And here I'm saying plotting two different errors. One is the training error, which you can see here. After a certain number of iterations, as certain number of epochs that Professor Nain was talking about, you see that the error rate becomes very normal. It gets to almost zero, while the network starts behaving very erratically when it comes to the validation part. So validation part is something that you don't show the network before, right? So if I have 10 pictures of dogs, I probably use 6 pictures to train the network, and then 4 other pictures of dogs I've not used it at all, and then I'm going to use them for the validation. So unless you encounter the error that is quite small for the validation, you should not be confident about your network. Okay, so it's a very common thing. Many people report this training error. Training error has no real implication. So what you need to look for is you need to look for the validation error, and then subsequently the test set error. And here comes the idea of in the morning we discussed this slightly about this mean square error, right? The first part. I think you can all recognize the first part here, which is exactly what I showed you in the morning. We have this parameters estimated from the network, and this is your prediction. It's the ground truth. So what you're going to do is you're going to look at the difference between the two of them, and when you start doing this, then you encounter a number of problems because it's a simple L2 error, right? It's a simple L2 metric. So how can you deal with that? You introduce a regularization factor that comes in the last part. And what it does is, depending on the strength of the lambda, it helps you in preventing the overfitting part. So one way to deal with overfitting is to look at training error and validation error, and the second one is also look at this the regularization factor. And then there is also this other small thing that you should be careful of. Whenever you have this overfitting or underfitting, then you typically coming because of these two factors. One is the high bias that will lead to underfitting, and then you have very high variance, and then you have overfitting. So what we want is the goal of training any network whenever we train is to have low bias and low variance. So as long as you can control those two factors, then you can be sure that the network is going to be robust. Okay, so now we are slowly getting towards the generative AI part. Let's start with something very trivial. Something very trivial in the sense here you have the tokens, and then you can encode them as positions, typically in the text processing, NLP domain, natural language processing. And then considering these two as input embeddings and the positional encoding, what you could start playing around is to start playing around with what is called as scale dot product, which leads us to saying it's a self-attention mechanism. Right? Now, the architecture itself is very simple. It's quite simple architecture, but very elegant. When you look at them, you see that there are three factors. One is Q and K, and then there is V. And we will come back to this later when we discuss in the transformers. But here, the idea is that very similar to the architectures, but we are looking at patches instead of the whole image. Right? And then you have, if you can just extend the same idea a bit further, what you can end up is you can end up with even better architecture, which is called as multi-headed attention, where you have the Q, K, and B as in the previous case, and then you have multiple attention heads, and then you keep on concatenating with the base W0. Now, in the case of feed-forward network, you can see that it's very similar architecture, right? So in the previous image, I showed you that it flows through a certain path. Here also, you can see that it flows through the same path. You have the input, you have the dense layers plus ReLU, and then you have again a couple of dense layers, and then you have an output. Now, keeping the same idea in the backdrop, what you can generalize is you can go towards the transformer architecture, which is somehow like this, right? You have an input, and then you have multi-head attention, and then there is some adding a norm operations, and then feed forward, and then add a norm, and then you have an output. Okay, we will discuss about this later when we come back to the lectures tomorrow and after tomorrow. But this is to give you an idea on how the network architectures can be generalized. So you understand one architecture fully, then you can kind of take the same concept to different other architectures. Okay, so why do we have to go from linear regression to something more complicated? And then we also said that even after going to the more complicated architectures, we still don't solve a lot of problems, right? So that's where the transformers come into picture. So on the left side, you see that the transformers has a number of specific properties, such as CNNs typically use local receptive fields, right? And that's based on the kernels. Now, the idea of using the kernel is again going back to the filter. If you recall that figure that I showed you with the 4x4 grid, I put a small block that was 2x2 grid, which was convoluting different features, right? So that is typically to take care of your local receptive fields. And there is a good degree of translation invariance through weight sharing in CNNs. And they are also very sequentially arranged, right? You have multiple layers, so which means that there is feature extraction happening in a hierarchical manner. But what it fails is CNNs fail to capture the global context, and that's where the transformers actually come into picture, right? So they use both self-attention models to model the global dependencies. There is no bias for the locality, because there is no local receptive fields. And then they are also scalable for very large inputs, especially if you look at the success of vision transformers. More or less everything that we are using today are more or less built on these kind of systems, right? Vision transformers. And then you have the spatial relationship, and transformers are very good at that by keeping the spatial attention intact. Okay? Which we'll discuss even further in the later lectures. But the transition here is that, again, nothing that has changed very drastically. The key changes that has happened here is that the vision transformers replace convolutions with patch embeddings. In the case of CNNs, you take the whole image, but in the case of transformers, what you do is you divide the whole image into number of chunks, number of blocks, and then you process each of the block, right? So the main difference comes from the patch embeddings there. And then in the case of CNNs, we had to slide the windows all the time, right? So we had to move from the top left of the image to the bottom right of the image. And this we don't have to do necessarily here, because there is no concept of sliding window here, which also saves on a lot of computation process, right? And then because of the nature of these architectures, they are also very good at modeling these long range dependencies. So if there is some particular relationship in the global context, they are very well retained in the case of transformers. Okay, so just to conclude a bit on this one. So remember, AI is actually not just AI itself. It's a foundation. It's built on the foundations of statistics and machine learning. So to succeed in generative AI, you need to understand these concepts very well, and then you can approximate the data. Then you can learn the data, and then you can come up with new architectures. All right, so now we can go slowly towards the second part. How do we evaluate the systems? Should close this one. Yeah. Oh, sorry. Questions.
Second part, can I have some queries?
Sure, sure, sure. Please, please, please. Oh, sorry. I should have asked for questions.
One thing you asked, you told about L2 regularization,
Yes.
where you are adding some parameters
Right.
with the error loss function.
Right.
Now there are various type of regularizations which are existing. So how do you identify that in what type of thing which regularization has to be done? Is there any statement thing, or you just have to try and see which
You
is
have to try for your data. It largely is driven by the data, right? So if your data is having very high variance, even choosing L2 is a bad idea, right? So that's why you go to the more sophisticated losses like cross entropy loss or binary cross entropy loss. There are a number of different kind of losses like dice loss when you are doing the medical segmentation. So based on the application, you have to choose all the time. Yeah. So that's why if you look at any papers in this domain, right? So they also do ablation studies. So where they vary the strength of the parameters of lambda, and they say, okay, across all these different lambda parameters, we have such performance. And regularization, what I give you is like I give you a very simple example of regularizing with lambda, but there is very often what you do is you combine multiple loss. So you have L2 loss, you have binary cross entropy loss, and then probably you have some other loss, and you put all of them together with different strengths. So you say with 0.3 weight of loss 1, 0.2 weight of loss 2, 0.5 weight of loss 3.
So that also combine. You are just guessing and doing some multi.
You have to understand the data, and then depending on the type of the data that you have, then you have to use there is this very nice survey on all different loss functions. Maybe I could share one of those surveys in the later session. Yeah?
And one more question.
Please go ahead. Go ahead.
You have talked about the attention mechanism.
Yeah.
I'm not getting that. What is the main idea of attention mechanism basically?
We come back to that tomorrow, so I can show you some nice illustrations, and then you can get an understanding of that one. But just have the idea that the primary factor in CNNs and transformers is the attention. That is the major change. Okay. So what I'll do here is that I'll talk a bit about, just give you some rough ideas around these different architectures that we will discuss later on. But what we will cover in this course is some introduction to variational autoencoders, generative adversarial networks, diffusion models, some minor introduction to autoregressive models. But this session we will focus mainly on this last three aspects, right? So the training and evaluating, and then training generative models. How do we do that? Okay, so we have been talking about, let's say, the regular image processing computer vision tasks so far in terms of looking at the data and then how we use the data, how we train the networks and so on from morning. But what generative AI refers to is typically it's the models that can generate new data out of some samples, right? So we are having a system which has learned something. From that representations, we want to create something new. What are the typical examples? Your text generation. So if you are writing some text on your phone, very often you get this autocomplete, right? So the moment you are typing some characters, you get a suggestion for what could be the word. So that is a classical example of this. And then image synthesis. Many of you probably have heard about this deep fake, right? So what are we trying to do? We are trying to create new image out of some learned distribution. And then there is also bigger implications. I think one of the talks by Professor Nain will be on this aspect, how the GAN networks have been used for face recognition, where they will talk about image creation part. And then there is also this other creative applications, right? Such as in music composition, you can use it, you can create art out of it, and so on. But the idea here is that so far, whenever we are learning a CNN classifier, what we are interested in creating or identifying and defining the classes. So we want to say whether it's cat or dog, right? But now when we come to this part, what we are looking at is we are looking at learning the generative models using the joint probability of p of x and y or p of x. The notations are slightly one and the same, but remember that in generative models we are more interested in this joint probability compared to the discriminative models. Okay. And again, let's take a very something happened. Okay. No. Okay. Good. So before we jump into this detailed discussion, what I wanted to introduce you here was to simply show how all these generative architectures work, right? So far, up until now, we have been talking about this Z1, Z2, Z3. If you remember from morning, all the mathematical formulas that we derived was circling around this Z. Now, in the case of generative networks, what we are more focused, or what we'd be talking more, is how we use this Z and decode the outputs. Right? So that is where the training part comes into picture from morning, and from there we go on towards recreating the images, recreating the data in new way. So any data that you have, typically it's called latent space. Some people call it as embedding. Some people call it as probability, the joint probability, and so on. But everything circles around the same idea. You have some representation that is learned using some trained networks, and then from there you start creating something new. So there is a decoder block typically, and then you get the output. And what happens in the case of variational autoencoder? Again, it's a very similar thing. You have an input, and then you encode it to get that Z. And once you get the Z, then what you do is you try to decode it and then reconstruct it. So then you have two things, right? You have two signals. One is signal X, which is going inside, and then you have the signal X hat, which is reconstructed image. So now the idea here would be to, let's say, to measure how faithfully the encoder network, VAE network, is able to recreate the image. And again, look at the probability distributions here. So there is an input X that will give you the probability distribution Q. And then here on the decoder part, you have the same Z, but then you are reconstructing X, right? So we will discuss about these concepts in detail later, but at this point of time, just have the idea, right? In the case of VAE, you are giving some input and then you are reconstructing some output. What this one? Yeah. So the bottom part is the loss, right? So now here you can see that it's a bit more complicated loss. So where we have this scale divergence, which I'll talk about it later as well. But this is more to give you an overall idea of how the architectures are arranged. And now, just keep this in your mind. And now let's go to the next part. In the case of GAN, generative adversarial network, the logic remains very similar. So you have the generator, and then you have a generated X, and then every time there is a generated X, what you want to do is you want to discriminate it, how realistic it is, right? So, and again, the idea here is that you're not using the actual images, you are using something called as noise, right? So on this side, you don't have a sample data, you just randomly pick some values and then start reconstructing the images, right? And then every time you reconstruct an image, you generate an image, what you want to do is you want to measure how realistic it is, how closer is it to the distribution that you want to, right? Let's say it's like this the artist game, right? Two-player artist game. So every time somebody produces an art and then it's compared with the original art and they say, okay, it's performing good, and then you accept it or you reject it and then you redo the art. It's same like your school assignments, right? Every time you do the school assignment, if you're done well, it's accepted. If it is not good, it's sent back and then you redo it, right? And then that's the whole cycle here. Okay, I will get back to this later, but just a quick picture of other one. In the case of the GAN networks, we were talking about this noise that was Z. And then in the case of diffusion process, it's again very similar architecture. From Z, it computes some parameters, and then there is a next step, that is zt minus 1, and then again you're continuing further, and z2 minus 2, and so on. So you can have various lines along this, and then at some point of time you get a generated output x0. Now the commonality between the GAN and diffusion is that in the case of GAN you had a discriminator, right? So which could actually say and look and tell the difference between the generated image and the actual image. But in this case we don't have any discriminator. So we randomly go from the noise towards creating some content.
So if I'm saying ZT minus 1, so it is going to be a previous Z value that is going to affect over there.
Yes. So depending on the way you are talking, right?
The value which is going to affect over there.
Depending on the way you are going, is it forward process or is it reverse process, right? So you could invert it on the other side as well. The goal is that you start from the noise and then you construct the image on the other side.
So are you saying that ZT minus 1 is some value which was calculated at time t, then it is
If you want to,
which was calculated at next time. So
next time step.
Are we adding a time value in that?
Well, it's actually not time, it's the iteration number, right? So what iteration are we standing at? They say it in the steps, but typically it's the timestamp. Well, I would not say timestamp. It's actually step number.
Next improvement, next iteration of improvement.
It varies. It varies. There is no standard configuration. So typically you start seeing reasonable results after 1000 iterations. Somewhere around that you can see some sensible output. Okay, so we'll come back to this later again when we talk about this in detail. Now, if you still recall the ideas of RNNs, we spoke about this predicting the next output, right? And then there is this idea of autoregressive process, autoregressive generation process. And here what we are doing is that we give bunch of input and then we try to predict the next one. So here comes the prediction P4, X4, and then comes the prediction X5 and so on. So again, looking at the probabilistic approach, you see that it's nothing but a joint probability of all the individual probabilities, right? It's a summation of all different probabilities. Use cases again in the case of text generation, in the case of translations and auto-completion and so on, which we'll not be covering in this case. So it's a very wide field, it's a wide domain. You will need at least a couple of weeks to talk about that. So we cannot cover image and text, so we'll only focus on the image part. Okay, just to have a quick snapshot of all the architectures here, right? If you try to look at them from a bird's eye view, what you see is that in the case of variation autoencoders, you start with an input, you end with an output, x and x bar. And in the case of the GAN networks, you see that there is a z. From the z, you start producing some output, which has both generator and a discriminator. And then you have the diffusion models, which is also very similar to input and output, but the only thing is that you add a lot of noise and then diffuse the image, and then there is a output. And then very similar to that is the autoregressive architectures, right? You have starting token, and then you can keep on predicting the next token based on your trained models. So now we have at least an idea of what we are talking about: discriminative models and generative models. The morning part we discussed a lot about discriminative models, and now we are talking about generative models. So how do we evaluate them, right? So that becomes another key question. How do we first train and then evaluate, and then when are we going to be satisfied with this? So whenever we are doing this thing, so typical training pipeline in the case of CNN includes an input image, and then you have some convolution, some ReLU, pooling, flattening, and then depending on the fully connected layer output that you're getting here, you try to compute the difference between the prediction and the ground truth. This is the loss between y and y bar, right? And then as soon as you have this, then you backpropagate that delta. So which means you tell that, okay, now go back and update the old parameters, which does an update as shown in as shown in this block, right? Which is what Professor Nain was explaining in the morning. So the whole idea of propagating the loss back to the initial network, right? And then comes the the measurement part, right? How do we say that the loss is good or when the network is getting stable? So if you start with a simple cross entropy loss, in this case we take the cross entropy loss, but it could be any other loss, right? So the idea comes down to something like this. The back propagation is you have some theta parameters, and then the theta parameters get updated by using that alpha, which is from previous slide, right? So which is the same notation that we use, and in case of Professor Nate, she was representing it using W, and then it can be theta. It's a standard notation, it doesn't matter, but the idea remains the same. So in the case of back propagation, again, there are each layers have this propagation, a contribution to the propagation, and then each of them also update the weights based on the gradient descent, right? So this is the simple idea. And now if you go from CNNs to generative AI, what happens here is that, as I already told, in the case of discriminative models, which are typically CNNs, you have this probability of y given an x. So what is the probability that this is an image of cat given that I have this data, right? So that's what you are interested in. And then it's typically used for experiments on, not experiments, applications on image classification, object detection, and so on. But very often to train anything, you would need some label data. So the massive amount of annotations that you would need is the key to success there. But in the case of generative AI, what we are doing is that we are not interested in just the probability y given x, but we are also interested in the other probability learning the p of x given y, right? So now the subtlety between them is only that part. Whatever we are doing, we are trying to learn that probability, model that probability. Once we have learned that one, we can always subsample, right? We can cherry pick and then we can hand pick, do random sampling. Every time you are doing something, you are going to get new data, new generations. And some examples in this is the GANs, VAEs, diffusion models that we have seen so far. And in the case of applications, it also varies very widely. In the first case, we don't have any synthesis application at all. But in the second case, there are a lot of applications around synthesis for image, text, and audio and video. Okay, so now we have an idea about how the CNNs are trained and how the loss is being propagated in the backward manner. So what happens in the case of generative AI pipeline? So you have this latent vector, and then you have a decoder network, and then you have a generated output, right? Very simply put, these are the three blocks that are in the network. Now, in terms of architecture, here you can see that you have input, features, and a class, right? In the case of CNNs. But in the case of generative AI, it's typically you start with the embeddings, which is latent space, then you have a decoder, and then you have an output. So there is no class concept coming into the idea of generative AI. And in the case of CNNs, they typically learn to classify, but in the case of generative AI, what we're interested is how to generate the data. And again, remember the key difference between the two architectures there is that in the case of CNNs, we always use the convolution plus pooling to reduce the features and then extract the features. In the case of generative AI, we always use the attention and then we transpose the attention, which is also the transpose convolution, right? So that is the key difference. So if your application is on extracting some nice features for some specific applications, do not look into the generative AI, right? So that you would not succeed in any way. So then if you have these kind of different models, CNNs, I think somehow we have control. We can backpropagate the loss and then we can measure the performance and say it's good or not good. But in the case of this VAE models, what we first want to do is we want to learn to model the distribution. So once you have learned the distribution, only then we can do other things, right? So learning the distribution means that here also there comes the idea of this loss, but in this case we are looking at some other loss other than this cross entropy loss, right? So we look at the likelihood loss, we look at the adversary loss because we are interested in finding out what is the likelihood of this data representing what we want to learn, right? And irrespective of what architectures you're using, VAE, GAN, and flow-based architectures, diffusion-based architectures, they all are trained in this same order. For the case of training flow, very simple again. You have this training data, and then you create a generative model, and then you get a generated sample. But both of them have two different objectives, right? Each of them are specific for a certain application. And then comes the part of measurement. How do we say that some systems are better than the other? How do we say that which loss was working good for us? So then we have this classical metrics. Any one of you that have worked on this simple machine learning algorithms, you would have seen these numbers, right? So the TP is the true positive, and then TN is the true negative, and then FP is the false positive, and FN is the false negative. So as soon as you have these four numbers, it's nothing but a 2x2 matrix, right? So maybe I should have added one more slide. So you have your four matrix. So you have your true class, let's say real, and then let's say this is fake, this is true class, and then this is predicted class, and then here you have real, here you have fake, and then the number of the amount of data that you end up here will result in the those four matrix. So when it is real and then you have identified it as real, so that is nothing but true positive, right? And then it's the other one, which is fake and the fake. What does that lead to? It leads to true negative, right? And then here you would have false positive and false negative, right? So it's now it's a combination of these four things. Then you put them together, then you get different metrics. Okay, so then we have somehow some control on how to measure the accuracy of the CNN classification. And then here you have precision and recall and F1 score, depending on the applications you would want to choose what metric to use. In the case of CNNs, it's not just the numbers that we get, right? It's always some probability that we are getting. So as soon as we get the probability, you can have a thresholding function which says that, okay, if the probability is more than 0.5, then it is certainly a cat. If the probability is less than 0.5, then it's not a cat, right? So that thresholding can be done. If you don't want to do that, you could still simply model it as a even more sophisticated approaches such as likelihood functions and so on. However, most common methodology is this one, right? So you set a particular threshold and you say that, okay, below or above, then the class is like this. And then coming to this part of confusion matrix, I showed you this very simply here. So the true positive, false negative, and true negative. This idea is very simple. If the label is 1 and the prediction is 1, then it's a true positive. And if the label is 1 but the prediction is 0, then it is false positive. And then you have label 0 but predicted as 1 as false negative, and then in the other case it is true negative, right? So you have these four numbers, and then with these four numbers you can actually measure the performance of any CNN models. And then I tried to make a nice diagram, but the arrows did not obey me. So here you see how they are all interrelated. But what is also very important is this one. So to be very certain that your model is performing well, what we typically do is we don't go for just the numbers. These numbers can be very misleading. So what is recommended is also to look at this curves, which are called as ROC curve, or also you can invert the same curve, then you have this a DET curve. So what does this do? So you have typically these two distributions. Let's assume that you have the distribution so if you have this kind of two distributions here, something like this, and this is for all the true classifications. This is, let's say, true classification, and then this is the false classifications, right? So for each of them, you're going to get the probability. And then a perfect system will be able to detect between cats and dogs here, right? Because the distributions are very well separated. But what happens in real world is that you never have this kind of clear classification. So you always end up with a distribution that goes something like this, right? Now, in these four cases, so if you want to separate out this cats and the dogs, then what we want to do is we want to identify what is the threshold. So the ideal threshold would be something here, which means I'm approximately misclassifying so much percentage of cats, and I'm also misclassifying some amount of dogs. Right? This is the best case scenario. So now I could be more stricter. I could be, maybe I like dogs, so I want all the dogs to be classified well. So I can move this threshold here, unfair to cats. And then if I want to be fair to cats, and if I start liking cats more, then I can move the threshold here. Right? So every time you move the threshold, you can get a point there on that curve. And that curve is the curve that tells you how reliable your system is. Any system that is random will give you this performance, right? So the performance that is shown in this dotted line. And the system, a perfect system would go towards this one, towards 1 and then stay at 1, right? So the moment we start doing this analysis, then we can say that, okay, under what conditions I can trust the system. So what is the variability between each different split? So if you have one split which is giving you here in the training, let's assume you have 100 images of cats, and then you use 20 images for the training iteratively, and the first 20 images are extremely well, and you end up with a system that is performing here. And for the next 20 images, maybe it starts dropping down here. And again, for the third set of images, it drops down here, fourth here, and so on. So by doing such an analysis, you can see that they actually vary quite a lot, and you can estimate the average performance of this one. Okay, so whenever you are training, just don't end up using the accuracy metric, but also look at the ROC and TET. And then if you don't like this curve, what you could do is you could use the same numbers and then invert it. Right? So when you invert it in this case, what you're looking at is that it's the same false positive rate and the false negative rate on one side, and the graphs are generated from same data. So you see that it's exactly the inverse, right? So it's only tilted bottomwards, this case and this case. Okay, but both of them actually give you the indications of what your classifier. The goal in this case of DET is to go towards 0. In the goal in case of ROC is to go towards 1. What happened? Okay, so now we have the tools to verify how good the training has been for the CNN networks, and now how do we do it for generative metrics? Okay, in the case of generative metrics, what we would look at is, remember I told you generative metrics is all about, generative AI is all about this latent space, right? So it's all about probability distribution. So the metrics that we are going to use here are also these measures of how likely the model assigns the probability to real world, which again boils down to a simple formulation here, right? Remember in the morning I discussed about this Bayes theorem, where we had the probability of A given B, and it's nothing but a simple formula, right? Which is exactly here. It's the Bayes theorem. You can generalize it a bit. Probability of X given Z, and then the probability of Z. And since it's a discrete domain, you have to integrate it all over the distribution. And then is the second part, right? Which is very similar to what we are interested is to look at how well we have reconstructed the image. That leads us to this error, which is nothing but L2 error, x1 minus x minus x hat, and then you take the norm of it in 2, 1, whatever is your favorite norm. And then comes the third one, which is a slightly sophisticated version of this reconstruction loss itself, which is the Frechet inception distance. And the idea behind the Frechet inception distance is that you want to see how similar the data looks to the real data. So if I'm interested in generating the image of Mahipal, I want to make sure that it actually looks like Mahipal, right? So we are adding the aspects of visual similarity into this one. So this gets extended. It takes the actual form of this particular, this takes the form of this particular loss, then extended in this case. So you have the real data, you have the generated data, which is very similar to this one, right? So look at the commonality here. And then on top of that comes the other aspect, which is this additional here. And this takes care of how similar the data are to each other in terms of visual illustrations. Okay, so unfortunately, I don't have any fancy pictures to show this graphs for this case, because those metrics are typically single metrics that you're getting, right? So you can't really have this ROC analysis, DT analysis for generative AI. But then if you put a discriminator on top of that, you typically end up with something like this, right? So the applications of the generated data can be measured within different contexts. Okay, so what is that we are looking for in the case of discriminator based evaluation? In the case of discriminator based evaluation, we have these two distributions as I showed here, right? So you want to have the distribution as close as possible. So if I have a distribution that is generated, that is here, and then if I have a distribution that is here, this is fairly good system. It's okay system, right? But the goal is to have the distribution which is exactly overlapping. So the red line should be overlapping with the blue line here in this case. So that's why it's very often people go and look at the measures like KL divergence. So KL divergence measures the distance between two different distributions to see how far apart we are from real data and the synthetic data. Right? And then there are also different other losses, Jensen-Shannon divergence, and then there is also the use of Wasserstein distance, and you have a number of different measures that you can actually use to measure the difference between the two distributions. Okay, let's take a simple look at how the reconstruction loss looks like. Because we are very often interested in creating the images of Mahipal, right? So if you are creating the face image of him, we want to also make sure that the images are very similar. And in this case, in the reconstruction loss, you have these pixel-wise differences. So for instance, here is the first image, the original image, and I have reconstructed that here. And if I take a difference between these two, these are the 3 pixels that I can see. They're quite different, right? Actually, there is one more pixel here, but that is very, very little difference that you can't actually see in that case. As soon as you see this one, you can already see the drawbacks of this loss, right? So it's not really capturing everything that we want them to capture, but you already see it works, but it doesn't work in all the cases. So in the case of generative AI, what people do typically is that they don't bank upon one loss. They use multiple metrics to make sure that the system is working the way it should work. Okay? Okay, so I think we decided about some break at after 1 hour. Are we taking a break? Oh, we can take a break, and then maybe then I just summarize this one, and then we can take the break, and then we can continue with the next part later. Okay. What did we want to learn in this session? So we wanted to see what is the difference between the discriminative networks versus generative networks. We have an idea about this right now, so we'll go into the depth later on. But we looked at the probabilistic way of looking at data in the case of generative AI rather than the discriminative networks. And we also looked at some high-level encoders, architecture, GAN architectures, and so on. And then we also looked at some potential use cases, such as in the case of VAEs, we always go for, oh, something is happening. Okay. In the case of VAEs, it's always probabilistic latent modeling. In the case of GANs, it is adversarial training, where we are looking at the discriminator. Something is happening all the time there. And then diffusion is a classical denoising process, and then you have autoregressive, which is more for sequential predictions, which is not in the scope of this course. Okay, we'll not talk about that one further on. Good. Any questions at this point of time before we take the break? I know I put a lot of new buzzwords now, so don't be worried about that one. I just wanted to give you an idea of what we are going to talk about later.
Yeah, because each will be addressed
In dedicated sessions.
with examples. So this is just to make you familiar with the terms that you'll be coming across.
No questions? So everybody ready for coffee? Okay.